I am the Chengfeng from the Hong Kong University of Science and Technology. And it's my honor to, on behalf of the authors, to present our work about the deadlock detection in the Linux kernel. We all know that the deadlock is a very well-known and traditional kind of concurrency software flaw. And it typically happens when each thread inside a group tries to acquire the lock that has already been acquired by other threads, and resulting in all of them block or spin forever. In its tradition, the deadlock is also characterized by the cyclic lock dependencies introduced by the nested lock acquisition. For example, here are two threads, the T1 and T2. They acquire the log1 and the log2 in the opposite order, and leading to a lock dependencies between them, forming a lock cycle. User space deadlocks could be more familiar to us, but in the kernel space, the things are more complex. That's because the interrupt preemption in the kernel could introduce a new kind of the lock dependencies, which we refer to as the interrupt lock dependency here. That's because when a thread is preempted by an interrupt handler, it cannot be rescheduled until the interrupt handler finishes its execution. And as a result, any loss held by the preempted threads cannot be released while the interrupt handler is executing. Here, given an example, the interrupt handler will acquire the log2 while in the interrupt context, while the thread A has already acquired the log01. So in this case, there will be a lock dependency from the log01 to the log02, since while the interrupt handler is executing, the log01 cannot be released. And the interrupt lock dependency could lead to a new kind of the deadlock that we refer to as the interrupt-based deadlock. We give the definition here is that like traditional deadlock is also formed as a deadlock lock dependency cycle, and here at least one of the dependency is introduced by the interrupt preemption. And furthermore, compared with the traditional deadlock, the interrupt-based deadlock is much more dangerous since it happens under the interrupt context. And when it happens, the CPU will spin and block and forever, and will monetize the system, and all the other threads cannot be executed. And here we give further examples of the real-world interrupt-based deadlock in the Linux kernel, which is also detected by our static analysis tool that we will introduce later. The left-hand side shows that one thread first acquired the log1, then call into the calling function to acquire the log2. And such execution path will introduce a traditional nested log dependency order from the log1 to the log2. At the same time, on the right-hand side, another thread is also executing a function. However, while the log2 is acquired by it, the interrupt handler has not yet been disabled, so it's possible that it will preempt the execution and then continue to acquire the log1, and which will form a new log dependency cycle from the 2 to 1. And under certain concurrent scheduling, that these threads and the interrupt handler will block and spin forever, forming the deadlock situation. And the interrupt-based deadlock has been troubling the Linux developers for a long time. So to combat with it, the Linux community developed the runtime locking correctness validator called the LockDep, which has already been built into the Linux kernel for years as a kind of the runtime sanitizer. However, just like all the dynamic analysis tools, it has a slight limitation that it relies the test case and the external device or at least certain level of the emulation to drive the concrete execution. So this will result in its low coverage to find some hidden bugs, especially given such large concurrent execution space. Compared with the dynamic analysis, the static analysis has its advantage in terms of the coverage, and there has been a very long history of the static deadlock detection. However, all of these methods, they do not model and cannot detect the interrupt-based deadlock due to the ignoring of the side effects introduced by the interrupt preemption. For example, here is a deadlock program with 2 threads and 1 interrupt handler. The traditional tools cannot capture the log dependencies shown at the red line, which is introduced by the interrupt preemption. So it cannot detect the life cycle and finally miss the deadlock. So to fill in this research gap, we proposed the Archerfish, the first systematic steady interrupt-based deadlock detection tool. At its core, we model the interrupt-based deadlock with the concept of the interrupt-aware log graph, in which the two kinds of the log dependencies are modeled as two kinds of edge on top of it. And the interrupt-based deadlock can be modeled as the cycle formed by this edge. The system consists of 4 synergetic stages to construct the graph and to detect the deadlock efficiently. First, the system will identify the interrupt service routines, and then data flow analysis will be performed to analyze the state of the log and the state of the interrupt in the system to construct a compact summary, which can be used to construct the interrupt-aware log graph and to detect the log cycle. Finally, the feasibility validation can be performed to prune away some false positives and finally give the bug reports. The design of the system considers several practical challenges. The first challenge is how to accurately identify the interrupt service routine in the Linux kernel. Due to the large number of the subsystems in it, apart from a few of the standard API to register the interrupt service routine, just like the right-hand side figure show, there are also many subsystem APIs and the interface which can also do the same test. For example, the right-hand side shows the callback interface under the network subsystem that the start transmit field can be used to register a software interrupt. And furthermore, the different types of the interrupt service routines have different priority. And in the Linux kernel, the hardware interrupt has higher priority than the software interrupt. So it's also necessary for us to distinguish them to reason the interrupt preemption. To combat the challenge, our idea is that the public large language model has already been trained on the rest of the public data, including those of the Linux kernel. So we can naturally regard it as a Linux expert to generate a specification to identify the interrupt service routines. And this specification can be can be added as a supplementary to those standard APIs that can model by human from the documentation. To enable this, given an adjust taken function in the Linux kernel, we first traverse its DevU chain to collect its registration site. Then some textual information like the function name, the type, and the corresponding information can be used to construct the prompt query. Then we can let the LLM regard it as a classifier over the execution context of the interface to decide whether the function is interrupt handlers of a certain type or just a normal kernel thread. The second challenge is that given the interrupt preemption in the Linux kernel, the interrupt concurrent interleaving space is very large. And specifically, at each statement, each statement could be preempted by any interrupt service routines enabled inside the system. And the state of this enabling or the disabling could vary from different calling contexts. For example, here the one function is called from 2 calling contexts. And from the calling context at the left-hand side, the interrupt handler has already been disabled at the call side, so it cannot preempt the execution. However, on the calling context on the right-hand side, the interrupt handler has not yet been disabled, so the preemption here is possible. The example means that the concurrent interleaving space is also further enlarged by the context sensitive. To overcome the challenge, our idea is that we notice that the statement inside the same critical section, they already share the same log. So we can just regard each critical section as a compact unit when we consider the interrupt preemption, instead of enumerating all the preemption possibility in the large space. So based on the idea, we first use data flow analysis to construct the state of the log and the interrupt in the system. and then from which we can construct several compact function summaries. Specifically, for each critical session, we will maintain the set of the set of the intra-service routines enabled inside it. And for each log acquisition, we also maintain the set of logs that has been released, which will be used for construct the log dependencies as the evidence. And for example, here for the log that we maintain, for this log acquisition, we maintain the two summary to represent the state of the critical session and the action of the log acquisition and its history. While analyzing the caller function, the summary of the calling function will be reused, update, and finally inline into the caller function to enable efficient context sensitivity. And with the summary in hand, intra-log dependency can be established by performing a pairwise matching between each critical session as well as each log acquisition by the intra-handlers that are enabled inside this critical session. Like this in the work, the nested log dependency can be established by inspecting the state of the log set at each log acquisition site. And once the graph is constructed, a standard cycle searching algorithm can be performed to identify the potential deadlocks. And furthermore, not all the program paths that can lead to the log dependency are really feasible in practice due to the existence of the concurrent synchronization or the path condition. However, in order to validate such the feasibility, some heavyweight verification such as the SMT solving is required. And when considered such a large concurrent execution program space, the efficiency of the validation is also a problem. So combat is challenging. Our simple idea is that the validation path, the validation execution path we only need to validate the execution path that form the deadlock cycle. The validation is twofold, including happen before analysis to validate the synchronization relationship between the thread and interrupt, and the path condition solving to validate the path feasibility. For example, here only given deadlock cycle that we have already detected, we will locate the corresponding statement and then construct the corresponding path condition to be validated by the SMT solver. The implementation of the Archerfish is based on the LLVM framework and the Z3 SMT solver. Specification generation is based on the ChatGPT-4 model. We have evaluated on top of the Linux kernel version 6.4, and we have detected 76 new intra-base deadlock, and we wrote a patch to fix all of them and send them to the developers. They have officially confirmed 53 of them and accept more of them. And the 2 new CVE IDs has been assigned. In terms of the precision, the false positive rate is about 50%, mostly due to the reasons such as the incomplete path condition or the imprecise specification. And in terms of the performance, it can finish its analysis in roughly 1 hour with 40 GB peak memory. And the ablation study also shows that each component is effective to assist the system, such as the large language model can identify more intra-service routines with high precision to detect more deadlocks. And the summary design can save time and memory, and the validation can validate the false positive in an efficient manner. And the more details of the evaluation can be found in the paper. And that's all of the presentation. I will be happy to take any questions. Thank you.